Our last sample for Unit 3 involves a satellite for a satellite TV. So if you ever have had a satellite TV program, you've got a satellite dish on the side of your house. And if you've ever noticed, the orientation of that satellite dish doesn't change. And in order for that to be the case, the satellite has to be in the same position all the time relative to where your dish is. We call that kind of orbit geostationary or geosynchronous. And as it says in the sample, which is on page 260, the period of that satellite's orbit has to be 24 hours. It has to go around once around, just like your satellite dish goes once around in 24 hours. A quick conversion gives us 86,400 seconds. Two questions here. What altitude does this satellite need to orbit at? And what does its speed have to be? So if you go along with the sample in your book, that's all well and good, but they start with a formula that we're not privy to. We're not given it on the exam. So if you want it, you're going to have to figure it out yourself. So that's the way I'm going to do it. We know that the force that keeps the satellite in orbit is a centripetal force, and that's gravity. So we can start out by writing that the gravitational force on the satellite is a centripetal force. All right, well, what good does that do us? Well, we have an expression for the gravitational force between Earth and the satellite, m1, m2 over r squared, and I will define those terms in just a moment, right? We know that that is also a centripetal force, so it's equal to mv squared over r. So just to be explicit, m1 here is the mass of the satellite, m2 is the mass of Earth. So take a second, pause the video if you need to make sure that that makes sense. R is not the radius of Earth, r is the distance between the center of the Earth and the orbit of the satellite. So we start out with this. You can see right off that we can cancel the mass of the satellite and we can cancel one of the r's. So we get g m2 over r equals v squared, right? And then solving for r, we get g m2, which is the mass of the Earth, over v squared, which seems awesome, except for we don't know the speed of that satellite, so we've got to figure it out. We don't know the speed of the satellite, but we do know how long it takes to go once around. So we can write, as we have a couple of times for anything that moves in a circle, the velocity is equal to the circumference of that circle over the period. Now, we do know the period. We don't know the radius, but we can plug that in. So plugging in this expression for v down here, and remember we need to square it, which makes it a little less pretty. R equals g times the mass, again, of the Earth, t squared over 2 pi r, and that quantity is squared. And a little algebraic manipulation gives us r cubed equals g, mass of the Earth, the period squared, over 4 pi squared. And that's what they start with in the sample, which is fine, except for they're not going to be able to start that way on an exam. You need to know how to get there. So a lot of plugging and chugging gives you a radius, an orbital radius of 4.2 times 10 to the 7 meters. Now, if they ask you how far is that altitude, how far is it above the surface, you just have to subtract out the radius of the Earth, which is not all that big of a deal. Now, that was the hard part by far of this problem. Part B asks you for the orbital speed, but remember, the orbital speed is just once around divided by the period. So plug in the radius that we just figured out, divide by the 86,400 seconds again, and you get a velocity of 3,070 meters per second. Okay, so that problem is really pretty easy. Again, just realize that the gravitational force causes the motion in a circle. Set the big G formula equal to mv squared over r, and the algebra is more difficult than the physics in this problem. So that's it for Unit 3, and I'll see you soon.